Okay, so now we're on problem 7, A through B, and enter true or false for the following. So for part B, or for part A, I'm sorry, it asks, free radical chlorination of methane is endothermic in its first propagation step as it generates a methyl radical and HCl. So I just showed the first propagation step here with the methane coming together with reacting with the chlorine radical. And so that forms the methyl radical and the HCl. So looking at these are two radicals, we know that both of those are really unstable. So I didn't really look at those two for my explanation. I looked more at the methane and the HCl. HCl is a strong acid. Something that's strong is unstable, whereas this is not. This is a very stable molecule. Methane's just stable. It's a regular carbon with its octet. So when we end up with something on the product side that is less stable than something that's on the reactant side, it's going to be an endothermic process. So we know that this is true. So part A was true. Now we want to see part B. The kinetic product and thermodynamic product of cyclopentene with MbS are the same, neglecting the stereoisomers. So remember MbS is also called trace Br2, trace small amounts of bromine, and excuse me, and we use these NbS for allylic and benzoic halogenation. So here we have cyclopentene, which is something that is going to, when you have a double bond or you have benzene, you're going to be wanting to use MbS. So here we have a double bond, so it's going to be allylic halogenation. Here I'm just showing the termination step with where we have our alkene radical and our bromine radical that form. And the way we figured out thermodynamic and kinetic is the thermodynamic product is going to be the more stable product, or the more highly substituted Zaitsev product, so I put Zaitsev in parentheses. And the kinetic product is going to be the less stable product, or the Hoffman product. I'm sorry, I think I might have said less stable, or less highly substituted. I meant more highly substituted, and this would be less highly substituted. So now, going through this, no matter which way, I showed the resonance structures, no matter which way these add together, these two radicals add together, you're going to be forming the same product. So if I showed it adding to this one, we'd be getting bromine here, and if I showed it adding to this one, we'd get bromine adding here, which is the same exact thing, just kind of flipped around. So the answer for this one would be true. The products are the same. So neglecting stereoisomers, so we're not even looking at stereoisomers.